Hello everyone, this is the video lecture of section 10.3. This is the section about arc length and curvature of a space curve. Okay, in Calculus 2, section 6.4, you learned that when you have a curve, this is section 10.3. In section 6.4, if your curve is given by x equals f of t, y equals g of t. Okay, curve like this. Then the arc length L was calculated using this. Now, if we introduce the concept of position vector, if you consider this curve as the trajectory of a moving object represented by a position vector, now we can represent this curve just like this. This is just two-dimensional position vector. All right? Then your velocity vector is the derivative. So you're doing what we did in section 10.2 in two-dimensional setting. You can consider this special curve where z coordinate is always 0, so that it is stuck on the xy plane. Then this is f prime of t, g prime of t. And this is nothing but magnitude of v of t, right? This is just still right. Magnitude of v of t is speed. So time integral of a speed will give you total distance you travel along the curve. Total distance you travel is exactly the arc length of the curve, represented by this position function. Okay? So, because of this, we can derive arc length formula right away. So if you have a space curve given by its position function from A to B, which means parametric equation x equals f of t, that means x equals f of t, y equals g of t, z equals h of t. Right? This is the same thing. Parametric equation version. The arc length represented by the space position function will be, again, just speed, time integral of a speed. Okay, r prime of t is f prime of t, g prime of t, h prime of t, as you learned in 10.2. Derivative of a vector value function is obtained by taking derivative of each component function. And your magnitude of this velocity is square root of x component square plus y component square plus g component square. So you're going to get this is it. If you can write it dx over dt squared, dy over dt squared, dz over dt squared if you want. So anyway, we use the total distance traveled by a moving object whose position function is this to calculate the arc length of the trajectory curve. Alright? Alright, let's do one first example. Example 1. Find the arc length of the curve r of t equals t, sine t, t from initial point is 1, 0, 0 and I think 1, 0, 2 pi. What is it? So t means, i.e., t runs from 0 to 2 pi, right? Cosine t sine t come back to the same value from 0 to 2 pi. T, z-coordinate rises from 0 to 2 pi. What was it? X, y, satisfying circle equation, confining a circular cylinder while z coordinates steadily rising. So you're following helix. This is the helix. Okay. So let's use that formula we just learned. R prime of t is minus sine t cosine t 1. We need speed. This is velocity. Speed, vectors. Speed is not vector. Speed is magnitude. This square, and this square. The sine square plus cosine square is always 1. 1 plus 1, square root of 2 for all t. Okay? You know that this is for all. Upside down capital A means for all. So, our arc length, t runs from 0 to 2 pi. This one, magnitude of the velocity, speed function, which is constant function in this case. So 0 to 2 pi, 2 pi minus 0. Or a lot of times we might want to write it this way. Same thing, 2 times square root of 2 pi. Okay? Alright. Now let's consider some interesting trial. So this is one turn. So only from here to here, right? X and Y and Z. This is circular cylinder. This helix is, winding around. Starting from to here. For the exact same curve, the first one, I'm going to call it R1 of t, the parameterization we just did. T from 0 to 2 pi. What if I write it this way? R2 of t cosine of 2t and 2t. Then t runs from 0 to only pi. If you compare these two, in section 1.7, you learned that they cover the same circle, unit circle. It's just that this one covers twice as fast as this one. 2t. Your angular velocity is twice. Per given time, this covers twice the angle. Alright? You cover the circle twice as fast. Yeah, your z coordinate also goes twice as fast. So they will be on the same trajectory. It's just that if I measure time from 0 to pi, it just covers the same track in half amount of time because it goes twice as fast. But at least as a trajectory curve, these two vector functions go through the exactly same trajectory for these two time intervals. right? So if your goal is to understand the shape of the trajectory, not the motion which going through the trajectory, shape of the trajectory, these two should not give you any different results. For example, arc length of the curve must not be depending on your choice of representation. And let's check if that is the case. So with this one, R2 prime, you have to use chain rule, minus sine 2t times 2. 2 times cosine of 2t, and 2. Yes, as we expected, this is exactly 2 times minus sine 2t and 1. Alright? And magnitude of this, so speed function, 2 times the magnitude of this. Sine square of 2t, cosine square of 2t, plus 1 square, 1 plus 1, 2, 2 square root of 2. Twice as fast, right? As I explained. So your arc length is from, now t runs from 0 to pi. And your speed function is 2 times square root of 2. 2 square root of 2, t, 0 to pi. Yes, 2 square root of 2, pi. Same as this, as you expected. So arc length is not depending on parametrization. It is independent of parametrization. Okay? All right? Now, let's define the following. Arc length function. Definition. C is piecewise smooth curve given by f of t, g of t, h of t. And C is traversed exactly once as t increases. Okay? So it's not like you're going around. If you have a cosine t, sine t, and z equal to 0, this will be a unit circle in the xy plane. As t goes, it keeps rounding and rounding. In that case, you have to stop at 2 pi. Alright? Then it will cover every point exactly once. Okay? Or your curve doesn't intersect itself at all. So that as t goes, you never go through a point twice on the curve. Okay? That's what it is talking about. Okay? Then we define S of t as, and define, and then the arc length function S of t is defined by this, from a to t, r prime of u magnitude du, which is dx of du squared dy over du squared h prime f prime of u squared g prime of u squared h prime of u squared du. then so what does it mean? So let's say you're going through this. So this is a speed function time integral from a to t. So this is arc length during the time a to t, or the distance you travel from a up to t. So let's say if t equals 1, you are here, then this is measuring the distance from here to here. At t equals 2, if you're here, then s of 2 will be the distance from here to here, or distance you travel from the beginning, t equals a. Let's say, starting from 0, let's say a equals 0. Okay? And so, this is measures arc length up to time t, alright? From a to t. Or distance traveled up to time t. Okay? Arc length function, we call it. Alright? Now, if you take the derivative, this is a scalar function, it's a real valued function, ds dt, which is t derivative of this integral. What is it? Integrate up to t and differentiate with respect to t. Okay, fundamental theorem of calculus. So this is going to be the inside function back with replacement t, with replacing t replacing u. Okay? So there's a speed function. Think about it. Your arc length is measures total distance up to t, right? So rate of change of s of t is the rate of change of your total distance you make with respect to time. Rate of change of distance per time, per unit time, is exactly speed, isn't it? Right? If you keep covering 10 meters per second, your distance, right? Arc length is keep growing 10 meters per second. That means your speed is 10 meters per second, right? So the derivative of t derivative arc length function is nothing but the speed of the motion. Okay? Now arc length s can give you very universal parametrization in a way. We saw that parametrization of the same curve can be infinitely many. I could do cosine 3t, sine 3t, 3t, t runs from 0 to 2 pi over 3. You have infinite many ways. Out of all this, parametrization using arc length rather than time can give you one universal. Okay? So let me just do that and then explain further. Example 2. Reparameterize the following curves with respect to the arc length S. WRT stands for with respect to, the arc length S. Okay. A. R1 of t, cosine t, sine t, and t. B. R2, cosine of 2t, sine of 2t. 2t. So what is it? These two are two different parameterization of helix, circular helix, of one turn in the angle. Alright? Now, here, before I continue, let me check the recording. Okay, so let's reparameterize on this one using the arc length function you can get from this. So, A, your S of t is from 0 to t. Now R, we learned that this magnitude, R1, okay, let's do it over here. Again, we learned that R prime of t equals cosine minus sine t cosine t 1. So its magnitude of derivative speed function is square root of 2. So your S of t from 0 to t, square root of t du. So square root of 2t. S equals this. From there, t equals s over square root of 2. Now because t is between 0 to 2 pi, that means, okay, s is between, see, s equals this, 0 to 2 square root of 2 pi, alright? So anyway, so how do we reparameterize? Well, use this, solve for t. So that your R1 of t becomes here as a function of s. As a function, R1 of s will be cosine of t equals s over square root of 2. Sine of t, s over square root of 2. T, s over square root of 2. Okay? That would be your result. And s from 0 to 2 square root of 2 pi. Okay? So now, this parameterization or vector value function represents your position vector as a function of distance you travel. So this one we can describe like this. If I travel along the path 1 meter, I will be in certain position. Cosine 1 over square root of 2, sine 1 over square root of 2, 1 over square root of 2. If I travel along the curve 2 meters, I will be in 2 over square root, s equals 2 position. If I travel 10 meters along the path, I will be in the position at cosine 10 over this, 10 over this, and 10 over this. So just describe your position of each point on the path as a function of travel, the distance traveled by you so far. Okay? Now, let's start with second parameterization from the beginning. We learned that this was just twice this. So R2 prime of t, we already did that in the previous comment, right? And your s of t is from 0 to t, 2 square root of 2 du, 2 square root of 2t. Now this time, see, t was from 0 to pi, therefore s is 2 square root of 2 times. 2 square root of 2 times. S will be 2 square root of 2 pi. Right? Same thing. We saw that same curve, different terms is still total same distance. same total distance. Now, let's use S here. Then what do you get? From there, T will be S over 2 square root of 2. Plug it in here. 2 times S 2 square root of 2. 2 cancel. You still get S over square root of 2. Right? And sine 2t will be also S over square root of 2. 2t S over, and S is over here. So what do you get? This is exactly same as this. So, no matter which parameterization you're starting with, if you try to describe the curve with respect to arc length S, then you will end up with exactly the same representation. And which should be obviously, easy to understand if you think this way. Anyway, they are representing the same curve. If it is same curve, if I only measure the distance I travel so far and describe my position as a function of travel the distance so far, that's the only one way, right? You can't have different positions for the same curve. After 1 meter later, you should be in the same position, right? If you walked along the same path, okay? So, in a sense, parameterization using a arc length function gives you universal, the most natural parameterization of any given curve, okay? So when you, in a geometry, differential geometry, study of curves, people use this parameterization using arc length, because that is the most natural. And also, another thing is that if you take the derivative, what do you get? So, if you take the derivative, minus 1 over square root of 2 sine of S square root of 2, and 1 over square root of 2 cosine S over square root of 2, and 1 over square root of 2. Take out 1 over square root of 2. So what do you get? If you take magnitude, this one square, sine square plus cosine square 1 over, this is 1, sorry, take out this. This is 1 plus 1 square root of 2. 1. Your speed will be 1. What does it mean? Speed is always 1 if your parameterization is with respect to arc length. Now, when you say speed, you have to consider S as your time, but S is the distance you made, right? Given certain point. So basically, you are saying that when I travel 1 meter, that's time 1 second. So that means you are going through the path in a way that your time, number of seconds, will be exactly matching number of meters. All right, number of unit time is matching number of unit length. So 1 second later, I should be moving 1 meter. 2 seconds later, I should have been moving 2 meters already. So your distance function is same as t, your time. Derivative 1, right? So it is not surprising. So taking S derivative, if you want to consider this as a speed, that means we are considering s is time. So your distance you travel, that number is same as your time number. So distance d equals t. So derivative 1. Okay? So that means if you follow parameterization using arc length, and if you shooting a picture, let's say if you consider it's moving object, s is our time, not only arc length but also time, then the moving point is going along the curve, same speed, speed 1, all the time. Alright? It's not going faster and slower. Always speed 1 if you use your arc length as your time. Okay? So for many reasons this is important parameterization, but we don't go further. This is enough. Okay? Now we want to talk about curvature. So curvature. Let's say you have a curve here. If you have a curve like this, over here, we say that this is not curving slowly. Okay? Curving fast. So we want to say this the way it's curving is not as severe as here, right? So we want to say that over here you have a small curvature, over here large curvature, because you're rapidly changing your direction, right? So we want to measure how curved it is, curvedness, using a concept of curvature. So the more rapidly curved, the higher value the curvature should have, whatever that curvature concept of curvature is. Okay? So then how do we define this curvedness, so-called curvature? One way to approach is this. Let's think about unit tangent vector. And let's say you go through this curve unit speed. So let's say our parameterization is made of length, arc length. Then every meter, so let's say this is unit tangent vector. 1 second later you're here. Another second later you're here. So per second, your unit tangent vector changes just a little bit, right? That means the derivative of unit tangent vector is small, right? You know that t of t is r prime of t. So we divide by this to make it unit vector. R prime of t is a derivative vector pointing in the moving direction, tangent. Just in case this is not unit vector, we divide this one by some magnitude. So when the curve is curving slowly, then this should be small. But over here, what happens? Over here, unit tangent vector over here. 1 second later, you're here. That means per unit time, the change in unit tangent vector is large, right? So the more curved it is, the more changes you go through, the unit tangent vector goes through more changes per unit time. So the derivative of unit tangent vector must be higher. So we define the curvature as this. Now, if I use unit arc length, S is arc length, then the magnitude is 1, as I said. This is just r prime of S magnitude, right? Anyway, so definition. curvature of a curve is defined by the following curvature, kappa, denoted by kappa. It's not K, this is actually Greek letter kappa, which is precedent of alphabet K, kappa. So you take the derivative of your unit tangent vector with respect to S from here, all right? Not this. Okay? And take magnitude. We want to make a real number. So derivative of the unit tangent vector, magnitude of that. Okay? Where T is the unit tangent vector. Now, here you have to be careful. You find the unit tangent vector and take the derivative with respect to S, not time, T, if it is given different. If your parametrization is given anything other than unit, this arc length S, then, remark, T, kappa is not just T derivative of the unit tangent vector. Let me explain. If your parametrization is just any usual ones, any general ones, not necessarily arc length, so sometimes you go fast, sometimes you go slow. What can happen is, let's say you go through this one really fast, okay? So it took just 0.1 second from here to here. Then unit tangent vector changes a bit, right? From here to here. Some moderate change, right? If you, from here to here, this much of change, right? But if you go through this one really fast, like 0.1 second, then your derivative will be like 10 times this, right? Because your derivative will be rate of change per unit time. So even though the curve is changing slowly, but if you go through that part really fast, then still d prime of t prime of t can be large value, even though your curve is curving slowly. On the other hand, over here to here, let's say you go from here to here over 100 seconds. You slow down a lot. You go really, really slowly. Then over 1 second, you're going to move from here to very nearby. So even though curve is curving quite hard, but because you're going through that one really slowly, this can be very small. See, rate of change per unit time. That's why it is not possible to measure the curvature of the curve using the derivative of unit tangent vector with respect to time. You have to compare apple to apple, not apple to orange. So, only when you go through this one in same speed, you can measure curvature using the derivative of unit tangent vector. Now, the best one is arc length. When you go through the curve with constant speed one. That's when you use parametrization with respect to arc length. Okay? So, if you want to follow this definition, we have to find unit tangent vector as a function of arc length s. Then you have to go through this kind of, so you have to find the reparametrization after you find arc length function s. That can be very hard or impossible, actually, because that requires to solve s of t equals whatever function of t and then solve for t. You have to find the inverse function. Sometimes you cannot solve it. So it's conceptually very simple, elegant definition, but in practice, it's quite hard to use. Then how do we overcome that? Okay? So, this is how we overcome that. So look at this. Remark. So, if you take t derivative using chain rule, if you have this was represented as a function of s, right? Let's say t is, okay, derivative of outside function times derivative of inside, right? This is chain rule. Therefore, dt ds is dt dt over ds dt. What was ds dt? That was speed, right? This is speed, right? Speed function. Now that this one makes sense, you find the rate of change of the unit tangent vector and then divide by the speed. You are adjusting. If you got a large rate of change only because you go fast, you will have to divide by your fast speed. So it'll adjust, right? So this is great. So therefore, your kappa is magnitude of this. Magnitude of this will be magnitude of the whole thing. So this can be constant, multiple can be taken out. So that will be, what is it? Unit tangent vector derivative vector magnitude over r prime of t speed. Okay? That would be first working formula. We can use the given parameterization as it is. You just find unit tangent vector, take the derivative and divide it, its magnitude divided by its speed. That's all. Okay? So let's do an example. Show that curvature of a circle, with radius a is 1 over a. Solution. So a circle with radius a. In section 1.7 we learned that that can be obtained by a sine t. Okay? We can do two-dimensional. So, alright. So that's the vector function, position function of a circle. Unit circle centered at the origin. Okay, you're starting from here. You keep circling around counterclockwise. If you use cosine versus x, sine for y. Now, r prime of t is minus a sine t and a cosine t. Magnitude of this, square root of a squared sine squared t, a squared cosine squared t, factor out a squared, you get sine squared t plus cosine squared t, which is 1, so square root of a squared, so a. We're assuming that a is obviously positive to be radius. So your speed is a. Okay? And what is t of t? Unit tangent vector. We know that r prime of t is tangent here. Okay? We have to make it length 1. So u t of t by definition is r prime of t over its magnitude. So quantity is a, so 1 over a times r prime of t. So it's minus sine t cosine t. that's unit tangent vector. Now finally, t prime of t equals minus cosine t minus sine t. Alright? The magnitude of this, square root of cosine squared sine squared t. So square root of 1, so 1. So this is 1. Therefore, curvature, which is t prime of t over r prime of t magnitude, 1 over a. This one gives us very important meaning. So, when you have a circle of radius a, then your curvature is 1 over a everywhere, constant, right? If radius is 2, curvature is 1/2. If radius is 10, curvature is 1/10. But think about it. If you take a piece of a circle with radius 1, it's like this. If you take a piece of a circle with radius 10, it will be like this, right? Because center is way over there. That means you're going to see that this is curving a lot. The smaller the radius, more curved it is, right? Smaller the a, larger the curvature. So, your curvature is defined in a way. So if you can, at given point, if you draw a best approximating curve, circle there, that radius a, then you define the curvature of a curve at certain point as a reciprocal of the radius of the circle, which is best approximating that part of the curve at that point. Okay? You can prove that statement if you want later. So this is the meaning of curvature. The value of curvature is actually, it's not just randomly given. This turns out to be the reciprocal of the radius of the circle, which approximates the curve the best. The best approximating circles, radius is reciprocal, is your curvature at that point. Okay? So, we're going to continue further from here, alright? In the second part. This is the end of the first part of section 10.3. Thank you.